Yeah, this is the first time in making sure the audio works right here. Let's see. Let's turn this down. All right, so we got this, and we'll just have to talk a little loud, and I think figure out the rest of it when we go. So let's see here. All right.
Perfect. Just a couple minutes then, really just 1 minute. We can throw it over to our club president or any officer that's out there wants to update, and then we'll throw it over to Gus.
Sounds good here.
It's been pretty quiet on our end. Mostly talking about a lot of audio stuff, audio files. These guys, a lot of guitars and stuff like that. So a lot of that chat this evening. Been pretty quiet from the Elmer session. So if this goes well, hopefully we can start trying to do this again in the future, and we'll see how it works. So yeah.
Absolutely. Luckily, we have Aaron on this side who helped out with some equipment as well as the last minute. It's like, oh, we got to adjust it.
Very cool.
So we'll have the mic here, so you probably want to see me as well, maybe.
Yeah, there we go.
All right.
How's the projection screen looking? Good looking video, or?
It looks good. What does everybody else think? Look okay? Okay. Yep. Then we can focus on the presenter when that starts.
Yep.
So. I think there's a couple places that could be improved, like an extension cord. That would be a good thing to bring to something like this. Yeah. So it is. Again, everybody thank Aaron back here in the back corner. He did a great job at bringing some extra equipment and stuff, so that way this worked better than I was originally planning. So thank you. So, all right. Ready whenever you are.
Is that a handoff to me, or do you have something else to go in between here?
Do we have an club president out there, or?
Do you want to say anything, Jerry? You want to say anything? Okay, we'll give him the mic. So, yep, this is okay. That's it. Just talking to that. Yeah. Over there, Jerry.
Well, welcome everybody. See, we got a fairly decent crowd, so thanks for coming. We've got a couple business things to handle, and here a while back, the board voted on replacing one of our repeaters over station 4, and that's the 147.33, but seeing as how it's a little chunk of money, according to bylaws, we have to have membership approval. But just a little history: the repeaters, the GE Master 2, it's good radio, but big. The transmitter receiver is about that thick, and the power supply is equally that size, and they're quite a load. So our thing is we want to consolidate for a couple of reasons. We want to get some newer equipment, and also we're trying to consolidate over there and put get the 6-meter repeater in the rack, and doing this will give us extra rack space, and the repeater we're looking at it's a Kenwood. It's just like all the other. It's a newer model, but we've got a Kenwood up on Squaw. We've got one on St. Anthony's, and we got 2 of them up on Centennial Cone, and they've proven very good and reliable. And so, if there's any questions about that, I'll try to answer them. But then the bid price on it is $1,900 $72.80. And that's from Triple C Communications. If any of you know Doug Sharp, he's owns it, and give us a little break. Yeah, yeah, yeah. How many is it now? 65 years old. Yeah. So anyway, if there's any questions, I'll ask just for. Is anybody opposed? That's a lot easier, I guess. Anybody opposed to us spending $1,972.80? Anybody in the deck there? Anybody out in the field? And if I guess not, so we'll consider that passed. Thank you. The other thing I've been pushing, telling you about is the RM Ham's calling it the Summer Swap Fest, and that is August 24th over at Adams County. And you can go to their website, rmham.com, I think. Just search, is it com or org? It may be. And you can just search RM Ham. It'll have the details on there. Anyway, that's the date that we dropped. They went ahead and picked it up. We decided that it just wasn't going to work out financially and everything else for DRC to do the Ham Fest, so that's why we dropped it. Also, the every 4 years, roughly, Colorado's turn for the RMRL state convention, and it passes around between New Mexico, Colorado, Utah, and Wyoming. Sometimes Wyoming bows out, but anyway, this year's Colorado's going to be over in Grand Junction. They've got special rates on rooms, and encouraging everybody to go. We're going to, Kathy and I and Lance and Gene Wilson, we're going to take the train over. So that'll be kind of an adventure in itself. So keep that in mind. It's October, I think, 24, 25, 26 in Grand Junction. And I think that's about all I got to really. What's everybody think of doing this? You like to do like this, or you probably do, or you wouldn't be here, huh? That's what I thought we just kind of did. Well, we did a negative vote. Anybody's opposed? Anybody opposed? And nobody's opposed, so nobody objected. So, any questions for me or about the club I can answer? Otherwise, we'll go to our program. Thanks for coming. Okay.
Perfect. Thank you. And
All
you
right,
may want
good
to
to go.
pin the video, or we did test sharing. Gus, if you want to go ahead and reshare your screen.
Yep,
Yeah,
I'll make sure it's.
getting ready to do that now. All right, let's give it a whirl here. Got to go to screen 2. And it should be sharing now. Are you seeing the primary screen?
Yep, we're good on this side.
Okay.
Yep.
I'll get a few things out of the way so I can see what I'm presenting here, and we'll be good to go. All right, I'm Gus, KB0YH. I go by Gus on the radio. Real name is August. My family and friends call me Augie, so any of those names work for me. If you want to ask a question during the presentation, feel free to do so. And I'm not even sure you know what the presentation's about, because I didn't see any information that described it or even told you who was presenting it. So if this is a surprise to you and you're not interested in this stuff, you're free to disappear, whatever you want to do. The presentation is about the things that affect the performance of a small transmitting loop antenna. And I've done presentations for the QSO expos that were done during the during the COVID-19 days. And I've done 2 or 3 presentations, in fact, there. And I've written some programs that are designed to help with the design and construction, well, not the construction, but the design of a small loop antenna, or as it's more commonly known, a magnetic loop antenna. So this is for those of you who either are restricted in what you can do on your property or wherever you're living, and it's actually looking to the future for many of you who, if you have to move out of a large property into a smaller location, may be very limited on what you can do for antennas. So I'm hoping that this will be of some benefit to you. First of all, I've always said this at the beginning of any of my presentations: if you could put up a full-size antenna outside in the clear, do it. There's no need to mess around with a loop. You don't need one. Unless you're interested in doing something like learning something new, helping a friend, or whatever. Or if you are limited on space or restricted by covenants or anything like that, then this is the way to go. I talk about legal issues, but I also mention the peace in the family issues. That's always a consideration. I know my wife here has been very kind to me over the many years we've been together. Not only here for the last 38 years, I guess it is, or so, but in other locations where I've had antennas outside. But not every wife is so forgiving or accommodating. And so count your blessings if you have a situation like mine. Is there a difference between STLs, small transmitting loop, and magnetic loop antennas? And the answer is yes and no. The reason is small transmitting loop is basically the same thing as a magnetic loop antenna. If you just look on it as a sending and receiving antenna, but the size is the issue. A true small transmitting loop antenna is 1/10 of a wavelength long. That is the loop conductor, including the capacitor and anything else that makes up that loop path. It's a series connection of the capacitor and the loop. And so you have to count the foot or whatever it is for the capacitor as part of that length. In any case, that's got to be 1/10 of a wavelength or less. Actually, it's about 0.085, but the common talk about this in any of the publications you'll read anywhere typically says 1/10 or less lambda, or the wavelength. The reason for this is at a loop of 1/10 of a wavelength or shorter, the constant current and phase is the factor that's good for the antenna. It does a couple of things, but having a constant current that is the same value no matter where you measure, and the phase is the same throughout. There's no phase difference from the beginning to the end. And this produces a deep and narrow set of nulls. They're broadside to the antenna. If you think of the loop as a bicycle wheel, the axis, looking through the axis, those are the nulls. And then the direction of the antenna, forward and back, is if you're traveling on the bicycle, you're looking straight ahead and back. Now it's what we call a fat wasted figure 8 pattern. And as you go to longer wavelengths, that is, if you go between like 1/10 of a wavelength and 3/10 of a wavelength, you get into the region that is typically referred to, well, the whole region is referred to as the magnetic loop. But between the 1/10 of a wavelength and 3/10 of a wavelength, what's happening is the current becomes a little bit less stable, the phase alters slightly, and that reduces that makes the nulls shallower and a bit wider. They're actually very deep if you're in the 1/10 of a wavelength or less, but they get a little bit fatter as you go to longer lengths on the loop conductor. But it's still a useful antenna. Most of the commercial small loops that you see advertised, when MFJ was in business, they're no longer doing this sort of stuff, but the manufacturers, there are several major ones now that are doing a pretty good job of making antennas, and they typically run in the range of 1/10 to 3/10 of a wavelength. Now I seem to have lost my mouse, and I have a feeling I'm a little bit underpowered on this. Oh, okay. Let me get that out of the way. And if I click on here, that'll do it. What's going on here is there's some design software that I've put together. If you do the math in the antenna book, the ARRL antenna book, there's a pretty hefty set of math formulas that you have to use to design the antenna. You have to know a few things about what are good places to start, but as you go through, you're going to find out that if you do this one time, you'll be successful perhaps, or you'll have some stumbling along the way. But let me get this thing out of the way here. Okay, the problem you get into is that you won't want to do it a second time. There's so much math there that if you make a small change, you've got to go through a whole set of formulas all over again. Why not put the computer to use and have that help you do the job? So that's what I'm doing here. What I have is a little program that I call STL Calc, and STL, small transmitting loop. It encompasses all of these antennas, STLs and what we call mag loop antennas. And as you can see, there are two components to it. There's a main window, and on the main window, there are places to put in the specification values. There's a place for selecting what units you're going to use, what loop length you're going to use, what loop shape rather, and also what conductor. You're going to use copper, you're going to use aluminum. There's a benefit to using copper. It's about 60% for aluminum versus the copper in terms of conductivity, and that reduces the efficiency and the overall performance a little bit. However, the aluminum may be more convenient to work with. That's up to you what you choose to do there. I'm doing this in the presentation using my 2.1.1 version of the program. However, I've recently released 2.3, and that updates a few things, but the basic information here is the same for both. And at the end of this presentation, I'll just give you a brief look at a few of the things that have changed, actually improvements, and one correction to improve some safety in terms of access to files. The program is written in Python. I did this back, I think the first version was back in 2021 when I was doing the presentation for the QSO Today Expo, and it was a way of learning to program in Python. I had never done it before. I've been programming primarily in C and related things over a number of years prior to this, but I had never tried Python. It had become quite a popular language, and I can understand why. And so this program is entirely done in Python and then packaged in such a way that you can go to the KB0YH QRZ page and choose for whatever operating system you're running. I run on Windows, a couple of versions of Linux, the Raspberry Pi OS running on a Raspberry Pi. I've got one on a Pi 4 upstairs and a nice widescreen, and the thing works beautifully. I use that as my primary programming platform these days. It's very convenient. It also runs on Linux Mint, which is a fairly popular version. I haven't done it on Ubuntu because they're getting ready to ditch their ties with Debian and do some other things, and I just don't want to get involved in that tangle. But if you're interested in one of those, or if you're interested in the Mac OS, I've run it on some Mac Minis, and I've run it on some in fact, I have a Mac OS. I mean a Mac Pro, the nice laptop, and it works beautifully on there as well. Now, there are a couple of things to think about here. When we talk about a magnetic loop, people get confused or they think things that aren't true. No magnets whatsoever. And the other thing is the antenna does respond to the electric field as well as the magnetic field. Some people say, well, it doesn't hear anything on the electric field, so that makes the noise go away. That's not quite true. The noise goes away if you can focus a null on the noise source, but it's still, the antenna still responds. However, the magnetic field dominates in what's called the near field of the antenna, and that's why it has its name. Also, there's some people that think it's a magic antenna. There's no magic, but I'll tell you, there are a couple of times when comparing an antenna like this, a little one, let's say a meter across or a yard, I'll speak in English or imperial terms for the time being, that small loop running on, let's say, 20 meters can sometimes beat out a log periodic or a three element Yagi antenna or a vertical or a dipole if the signal's coming in a direction and at an elevation angle which is good for the loop and not good for the other antenna. And so if somebody says, my loop beat out my Yagi, well, that may be true only because the loop was picking up an NVIS signal and the Yagi was reaching out too far and couldn't hear it. So it just depends on what the comparison is. But there's no magic involved, I guarantee you. So here's what we're going to be talking about, and I'll go through these in this order. The tuning capacitor is the first thing, and the reason is it's the most important part. If you don't have a good tuning loop, you're going to have a problem. A good tuning capacitor. The loop conductor and the shape of that conductor is also an important factor in the design and construction of these antennas, and I'll show you some ways to avoid problems. And then I get into a couple of other areas of interest. One is planar versus helical. By that I mean single turn versus multi-turn loops. And the reason I did it this way is because the antenna design function, the equations that are used are basically the kinds of things that analyze helixes versus single plane or single loop. And then we get into the coupling loop consideration. There are several different ways of feeding power into the antenna for transmission or extracting energy on reception. And the way I choose to do it is to have a separate, isolated, separate coupling loop that I put power into to transmit or extract power from the antenna to receive. And I find that works better than gammas and various other things, and I'll show you why. But those are the four major topics here. So let's begin with the tuning capacitor. There are several things that are referred to as bread slicers. You want to avoid the typical bread slicer, which is the kind you'd pull out of an AM radio or some other small device. Some of the things you could buy from MFJ or other places to do antenna analysis used bread slicer type capacitors. They weren't trying to transmit. That's the reason why they got away with that. But the split stator type is what we're going to be favoring, at least if you're going to be using these kinds of air variables. And by the way, butterfly and trombone style are just two different names for the thing which is a split stator capacitor. I'll show you a couple of examples here quickly. Depending on which one you're using, they can have some pretty high noise, not noise loss introduced, and also they can introduce noise as you tune, depending on how they're constructed. So you have to be careful there. The other thing is they're subjected to environmental factors that you can't really control, humidity, temperature, if you're putting the antenna outside. And unfortunately, these plate type slicer capacitors are susceptible to changes in those parameters, and you just have to live with that. You have to readjust the frequency from time to time, the tuning to match the frequency. But this is typically the lowest cost antenna tuner device, and so they're commonly used. The vacuum variable, I call it the king, and the reason for that is it's very low loss. They're extremely stable. I can give you an example. One of these, I put out a loop, a 10-foot diameter loop hanging from a tree branch in my backyard. The capacitor was way up at the top, the coupling loop down at the bottom. I tuned it up. I set it on 3868, which is a frequency that I get on with a lot of friends of mine in the morning on 75 meters. And I tuned this thing in the middle of winter to the middle of the audio passband, if you will, on 3868. So down about a kilohertz and a half in the frequency. I adjusted it for essentially 1-to-1 SWR at that point. And I let it hang there for 1 year. I used it virtually every day. Some days I missed, but I used it for a year. Sunshine, cold temperatures, ice on the antenna. The vacuum variable was sitting out in the air and nothing around it to protect it. And that thing stayed right rock solid all the way through that year. That tells me that's a pretty stable antenna using that vacuum variable. However, these things are expensive. You have to expect to pay several $100s. If you buy a brand new one, $800 or $900. If you buy a used one from a company, MGS, for example, Max Gain Systems in Atlanta, they get surplus vacuum variables, and they sell them at prices around $250 to $300, which is a bit more acceptable, at least to my budget. Here's some examples of split stator capacitors. The one on the left is the typical you'd find, although this one has the two stators on opposite sides of each other. They're essentially half sections, if you will. And on one side, it's close to you. On the other side, it's far away from you, the way we're looking at this. And then there's a rod that goes through the middle, the shaft, that holds the rotor component. And the reason you can use this kind of an antenna tuner, a capacitor for the tuning, is there's no place where current has to flow through a sliding contact like you would have in a typical 365 picofarad AM broadcast band kind of a tuning capacitor. The one on the right here is a butterfly, called that obviously because of the shape of the rotor component. The stator components you can see are on either side there. The rotor component looks like a butterfly wing and has that fancy name, but it's just a split stator capacitor. It only thinks it's better than the rest of the capacitors. By the way, interrupt at any time if you have a question. This is where we get into the place where you might want to know more. On the left here is a trombone style capacitor that I built from parts. Internally, well, if you look at the aluminum tubing at the top there, that goes up through the box. This is in a plastic box that I built. I bought a big sheet and I had it cut into sliced pieces, and then I sliced those down to shorter pieces to make covers and so on. But anyway, those are the stator components, and that's why it's a split stator, one on one side, one on the other side. And those would run up through there and then attach on to the ends of the loop. Inside, there's some PEX. You can actually see it in here, just a little bit of an overlap here where I'm moving this pointer. And that's PEX. That's good stuff that's used in in-floor heating type systems, radiant heating systems, and various other things. And you can buy that in either stick form, tubing, or in rolls of tubing, depending on how you're going to use it. I buy the stick form and then I just cut the pieces that I need. The reason I did that was that fits perfectly inside the aluminum tube. And then I found a size of copper that fits just inside the PEX down here. So it makes a nice snug fit. And then notice the capacitor is tuned by adjusting the depth to which this squared off corner U shape it slides all the way in to make a higher capacity value and comes out to reduce the value. There's some yellow fiberglass rods in here. Those are just stabilizers. What happens is when you pull that U-shaped piece away from the main stators, it tends to wobble a little bit. It's moved by a threaded rod, and the threaded rod goes down into the bottom. There's a compartment there where there's a motor, a DC motor that drives it one way or the other, depending on whether you're trying to go up and down or down in frequency. But those yellow rods, they're stabilized so that it doesn't flop back and forth and cause changes in the capacity. Here's a vacuum variable. This one is relatively small. It's 110 picofarads maximum, 6 picofarads minimum, I believe. And it's good for 7.5 kilovolts. I use this on one of my loops. I've built quite a few. You'll notice later on. I'll show you some. But anyway, this is the box in which the vacuum variable is located. It's also, in this case, the box into which the signal comes. There's a connector down here at the bottom, and there's a capacitor that couples the RF through to the coupling loop, and there's an inductor here, the choke. In this case, it's 100 microhenries, I believe it is, that's separating out the DC and feeding that to the motor control circuit. Here's the DC motor. Here's a block on here that travels back and forth. It's pushed against the bottom board, and as it rides back and forth, it triggers one switch or the other depending on when it reaches the limit on one direction or the other. In here, I've used a belt and pulley kind of arrangement to give me about a 3-to-1 reduction in speed. This motor turns at about 80 turns per minute. This cuts it down by 4, and then this is a 10-turn vacuum variable, so I can get some pretty good tuning there. And with a low voltage on the motor, I can do close-in tuning adjustments, and I can use a higher voltage to drive the motor faster and do slewing between bands more quickly. In any case, that's those are the kinds of capacitors that I use in my designs. Any questions so far? I'll assume that you're all asleep, or I'm doing a perfect job here. Okay, making good connections is part of the business associated with the capacitor. You can have a great capacitor, but if you don't make good connections, you're going to have some problems because you're introducing losses, and losses are the killer for these kinds of antennas. So you want to minimize the number of connections that you have. And the other thing is, when you're putting them together, make sure that the kind of contact you make has plenty of surface area, no room for oxidization, and a good compression so that you get a nice tight fit there, and good, because you're going to be having to handle lots of current. The implementation that I'm showing in this picture is by a guy named Joe Street, VE7VXO. I talked to him on the air one day, and I went to his QRZ page, and I saw some of the antennas he built. He does a really nice job. And if you want to make good contacts, here's a good way to go. These are blocks. It's a kind of a plastic block with a metal cap on it. And there are 2 blocks. This one over here on the left and the other one over on the right have a piece of PVC. That's just to be a placeholder right now for these pieces of copper. But in any case, that's where the tubing would come in. This would be one side of the tubing that's being used, or the whatever is used for the conductor. This would be the other side over here. You get a nice tight clamping mechanism. This is copper sheeting, and it's cut in such a way that this is the width over here, but it's actually wider. It's wider here at the vacuum variable, and it's wider over here at the tube that's being used as a conductor for the loop. And notice something here. These 2 are the same size. These 2 guys are different in size, and because of that, there's a shim underneath here, and that's because the sizes of the connections on the vacuum variable are not uniform. They're different dimensions, different diameters. So you have to compensate for things like that. But this is a great way to make a good electrical connection, reduce the number of connections, and provide a very stable platform, especially for the vacuum variable, so that it doesn't crack the glass or do any other damage to it. Now here's an example of a listing rather of the things that you can specify. Units, I use imperial or metric. Imperial is the correct name to use. People say English, but it's not just English. It covers a lot of other countries that are non-English speaking. And then metric basically covers the rest of the world. And there are programs out there already that do this kind of work, but they're a little bit sloppy about it. I made it so that you can put information in imperial and then switch it to metric on the fly, or go back the other way depending on what's available to you. And it tries to keep track within 3 decimal places, I guess it is. You might see a tick of 1 up or down in the 3rd decimal place if you're switching between them. I'm going to try to up the precision of the calculations to avoid that, but it's no big deal. It's a tenth, a mil, if you will, out of many inches. Okay, the shape circle, octagon, hexagon, and square are presented here, and circle is the best. Anything below that in this order gets worse as you go down. However, octagon and hexagon are actually pretty good at simulating a circle, at least in terms of the overall size, the area that they encompass, just reduced a little bit. The problem is you can make a circle out of a continuous piece of copper or aluminum, but if you make an octagon or a hexagon, you're probably doing it by soldering pieces together or welding pieces together, and you've got to make sure all those welds or solder joints are very well done because they can introduce losses. And then the copper and aluminum are the choices on the conductor, and I recommend you try to use copper if you can. I've used a little bit of aluminum in some of my designs, and you'll see a few to show that I'm not a total bigot about that sort of thing. But here's an example. See, the one on the right here, the octagon, is one of the very first ones that I ever built. Actually, it's the second one. The first one I built was a little flat stock aluminum, but this is the first one I made out of copper, the first one that I made with a trombone capacitor, and I didn't have a stabilizer on this one. And when I was tuned to the lower frequencies, it was nice and stable. At the higher frequencies, the wind would blow and change the frequency, change the tuning at the frequency I was on. Here's a square. I tried this just to see what it was like, and I made a big mistake here. These tubes are very long, and the inside over here, if you have the U-shaped trombone slid down low here to tune to a higher frequency, that is, reduce the capacity, you get into a little bit of a problem because all of that metal is part of the loop length. And the problem with a trombone style capacitor is this: as you try to go to a lower frequency, you're trying to up the size, the value of the capacitor, but at the same time, you're reducing the length, which is working against you when you're reducing the length of the overall conductor. And as you go to higher frequencies, lower capacity, you're pulling the thing out and you're making the loop longer, which is, again, the opposite of what you're trying to do. So the overall effect there is it tends to reduce the tuning range of those trombone style capacitors, and that's why I tend to go with vacuum variables, even if I don't need to run high power. All right, here's an example of what happens when you run the program. The STL calc program allows you to specify all those things I talked about. Here we're saying we've got a loop length of 16 feet. We've got half-inch diameter conductor. The conductor, by the way, is copper. It's a circle, and we're using imperial measurements. The frequency of interest here is 7.1 megahertz, so we're in the 40-meter band, just a little above the digital portion, or right around the digital portion, and we're putting in 100 watts. Notice over here I've got some internal losses showing, about 40 I show on this one, and I've got some additional loss here. This is a throwback to an earlier version of the program, and I no longer recommend you use this. Do all the work in the internal losses, and that's done using a technique that I'll show you shortly, a little further down the line. What I've done here is I've taken a sample, all of the same input information here, except for the conductor. Conductor goes from 1/2 to 1 inch to 2 inches to 4 inches. My reason for doing this is I'm trying to show what impact that has on some of the important performance aspects. I do that using the export record function. That's this button right here. The first time you use it, you want to make sure you don't have a file that it's going to write to. You want to start fresh. But if you do start with something in it already, you can always remove it later on. But the export record feature takes all the values, everything, input and output, and saves that to a file. If the file doesn't exist, it's created. And the first line that's put in is all of the header information. The second time you do a record save, it produces only data values. The first time it does that header line and then the data values. Everyone after that is just data values. And so we're going to have 5 lines in the resulting file and 4 of them are for these values, and 1 is the headers. What that ends up doing is giving you a spreadsheet that you can use. And in my case, I'm using LibreOffice Calc program. You could also use Excel. I've used a number of other programs that do this sort of thing. But anything that gives you a spreadsheet can probably produce charts of various types. In this case, I'm producing bar charts, and the reason for that is these are discrete items, discrete values. I could go at a lot of between values here, and then I'd use a line chart instead, but I'm just doing these 4 discrete values. And notice I'm comparing bandwidth, voltage, the efficiency, and the current. The one that intrigues me the most, obviously, or that I'm interested in, is what's the change in the efficiency, and that's shown by the yellow bars here. And the efficiency for a 1/2 inch, 22.6%. When you go all the way up to 4 inches, you get to a 42% value. That gets interpreted in different ways, but that's a change of some, 20-some percent, but it's also a plus 2.6 dB advantage. Keeping the same conductor length, the same capacitor values, and so on, you've picked up almost 3 dB, or almost doubling the power effect of the antenna. So that's a distinct advantage if you can go to larger diameter conductors. However, those tend to get heavy, and you may want to stay with the smaller size and compensate in other ways. We'll talk about what the real loss is here. If you can tolerate the 2.6 dB of using the smaller conductor over the larger one, then go for it. In fact, most of mine are sitting in here at around the 1 inch value. I tend to use 7/8 inch hardline, and I do that because it's fairly rigid. It makes a nice circle and holds it with minimal superstructure, and its resistance at RF is quite low, which is a good thing. The loss resistance, that is, and so that's my sweet spot. But use whatever floats your boat there. Now, if I want to do a shape evaluation, I'm going to look at each of these in turn. I'm going to have to do something first to make sure that I take into account losses introduced by the soldered or welded joints in the antenna. Depending on the number of joins, you can have some pretty significant loss. So what you do is you go to configuration and then loss resistance estimates. These are only estimates. And you're going to put in values over here in fractional form, fractional inches in this case is what we're using. The I'm sorry, in terms of ohms, fractional ohms. But anyway, the capacitor loss, that you can get a pretty good estimate by reading the literature about the particular capacitor you're using. There's generally information available. A vacuum variable typically runs somewhere between about 8 milliohms on the low end to 20 on the top end. So this would be a good vacuum variable. I mean, a poor vacuum variable, but a good, bread slicer type capacitor. Now, the number of connections is shown in here because I've chosen circle. I'm only going to have 2 connections, or at least I'm hoping that that's the case. If I have more, I can compensate for that, but it assumes 2. You put in the value for 1, and it'll multiply that value by 2. And this is just a wild ass guess here because I don't know in advance, but I, over time, have figured out for different types of a construction what these values will typically be in terms of how good a job I do soldering or welding or whatever. And joint loss over here doesn't matter because it's multiplied by 0. I was describing this incorrectly. These are the connections to the capacitor, and if you do these jobs well, you can make that resistance value very low. If you have a soldered connection on a octagon or a hexagon or whatever, then that will be here, and you get multiplied by the number of joins that there are in that particular shape. Then save and close. It puts that value in, saves it in that field up there. You can't write in that field. You have to populated by using this modal dialog. Here's the result then of going circle, octagon, hexagon, square. That's the only thing that's changing. We're just changing the control value on the input side over here. Everything else remains the same on the input, but you'll notice the output varies. For example, for a circle, we've got an antenna Q gets calculated. Let's do the bandwidth. That's a better thing for what we're trying to show here. 4.77 kilohertz for the circle. Now, it's actually going to change and go to 6.19 bandwidth for the octagon. You say, that's better, that's good. Well, it is and it isn't. The reason it's good is because it's a wider bandwidth and make tuning easier, not quite as touchy. But what's also happening is your efficiency dropped from 29% to 24%. Not a killer, but it's lower performance. So you have to decide whether that kind of a drop in performance is good versus the change in bandwidth. A lot of people opt for the bandwidth because they get to tune more easily and they can change frequency and not have to adjust to a new frequency every time they move 5 kilohertz or whatever it is, or in this case, 6. You'd have to tune to the middle or as close as you can if two stations are near each other and you're trying to swap back and forth between them. Going to the hexagon, things change a little bit. The bandwidth tends to narrow down a little bit again, and then it gets even worse for the square. And notice the changes in efficiency. We can actually see them more directly here. When you're going, after I've put the Excel spreadsheet or the Libra Calc spreadsheet together, I can produce this bar chart. And in this case, the efficiency shows up as this orange color thing here. It goes from 29.2% for a circle for the given 16-foot copper, 40-meter band, 100 watts. It drops from 29% down to 17.2, and that's a 2.3 dB loss going from a circle to a square. So the square may be easier to build and install somewhere, but you're going to lose performance by doing so. The story there is, if you can use a circle, use a circle. Okay, here's an example of a line chart, because this is a continuum. And what we're looking at here is what I call maximizing performance, or right-sizing your loop. That's what I said down here, right-size your loop for the band. In this case, we're right-sizing for the lower end of 15 meters from 21 to 21.2 megahertz. That'll give us coverage of the CW and the digital modes and so on. Narrow band stuff typically, but notice what happens here. If we go from, in this case, we're changing the frequency. We're going to do another one of these things, but in this case, we're going to have 5 stops along the way. I'm not going to show them all here because that just gets a little bit tedious. But notice here at 7.1 megahertz, the efficiency, I'm sorry, the loss, the yellow one here is the loss. The resistance loss goes up a little bit, but it's not tragic. And what happens with it, but it's really low. And fortunately, that's good in a way. We don't want too much loss there. But notice and by the way, the resistance values are shown on this side. The red is the radiation resistance in ohms. And it goes from a relatively few milliohms down here at 7.1 megahertz and rises gently at first and then rather radically as you go higher. So 17-meter performance is considerably better. And the 21 megahertz thing at 15 meters gets even better. Now let's look at bandwidth. Notice how the bandwidth changes also. Bandwidth very narrow down on 40 meters, but as you go to 15 meters, it gets quite large, up in the order of 3.5 kilohertz here, the way this is shown. I'm sorry, not 3.5, up to 100 kilohertz. These values over here for bandwidth and the efficiency are shown over on this side. So anyway, the top end bandwidth looks to be a little over 100 kilohertz, and the efficiency is actually rising pretty well too. That's the green line here, and you're getting up into the 90% range on efficiency, and even a little bit higher, a little over the mid 90s. You never get to 100% here. There is no such thing as a perfect loop. And by the way, these values, when I talk about efficiency, 100% efficiency means as good as you can get with a perfect loop, if there were one. And as I just said, there isn't one. Recognize that a loop by itself, if in a head-to-head comparison with a full-size dipole or a vertical, is already down by 5 or 10 dB, depending on where you are. Well, by at least 3 or 4 dB in some comparisons, and as much as 15 dB down, or maybe a little bit more as you go to the lower frequencies. The loop is always going to be at a disadvantage. It's a small antenna. There's no way to beat that. It's just the way it is. However, this antenna beats no antenna by an infinite margin. And so if the only antenna you can put out is a magnetic loop or a small transmitting loop, don't give up. It's a good way to go. Okay, before I start, single turn versus multi-turn, any questions or anything? If anybody's talking, I can't hear you.
We can hear
Okay,
you.
I'm going to assume. Oh, go ahead.
No, yep. Google Meet's been hearing you. Hopefully the live audience has been hearing you, but nothing so far. No questions so far.
Okay.
Yep, no questions on this side.
Okay, very good. Then single turn, what I call planar loops, multi-turn, what I call helical loops. And the reason is just because of the way the math works out. I'm using helical formulas over here. The single turn is the most common type. If you can use a single turn loop, do it. The reason I say that is even a 10-foot diameter single loop, if you can hide it in the bushes or in the back of a garage on the back door, on the back of the barn or whatever, it's a good way to go. It'll get the antenna out away from people and away from sensitive hi-fis and various other things. It's the easiest one to build. It has the highest capture area, and so this is a good way to go. I recommend it. It's most often used in the range of 10 to 30, either 10 to 30 meters or 10 to 30 megahertz, depending on which way you're going. The nice thing about the single turn, as I say, is it's easier to construct. It's just so much simpler. When you get into multiple turns, and I'm recommending, I show here, I support 2 to 5 with my program. I recommend 2, 3 max. 4 and 5 are just too difficult to manage and very inefficient, and I don't recommend those. The sweet spot is 1. I've done a lot of work with 2 and 3 turn loops and had very good success. I tried a 4-turn loop and it just drove me nuts, so I don't do that anymore. The capture area gets reduced with each additional turn, but it's not quite as dire as that sounds. If you cut the loop length, if you keep the loop length, the constant rather, and you cut the diameter in half by going to a 2-turn loop, you've got a quarter of the area for each turn of the loop, but you have 2 of those turns. So you've cut the effective area of the antenna by a factor of 2, not 4. So it's not quite as dire as it makes it sound at first. However, it is reduced with each additional turn, and you have to be careful there. The pitch factor is something that I kind of invented for my purposes here. I chose to do the distance between turns of a loop in terms of diameters of the conductor. And because to do it any other way makes really complicated math, and it makes the I/O, the way you handle I/O a lot more complicated in order to do the job correctly. And so this is the way I've chosen to do things. So when you go to 2 turns on the loop, for example, you end up seeing over here the pitch factor, which can range from 3 to 20. The number that I go to by default is 5. I have found that the sweet spot is somewhere between 5 and 10. Beyond 10, things start to get a little bit dicey. The inductance is going down or changing in ways that are not nice, and the off-axis behavior of the loop is such that you think the axis is in right through the middle of the loop, but it's really off by some number of degrees. And the more you the more you stretch the turns apart, the more that deviates from the axis. I do one of my loops right now that I have uses 5 diameters between turns, and the other one uses 10, and both of those antennas work very well. Here's an example of a single turn loop, and this was one of my early tests. I was actually testing this coupling loop here. I was trying to see what would be the best size for the coupling loop. It's typically 20% diameter. 20% of the main diameter is used for 20% for the diameter of the small loop. Now, the problem here is there are two factors. There are actually three. The length of this loop compared to the length of that loop, or whatever is easiest for you to measure. Typically, that's the diameter if they're both circles. That's one factor. The other factor is how close this loop is to the main loop, and are they in the same plane, or is one rotated from the other one? All of those things affect the impedance match. And so designing this coupling loop is a critical factor in getting good performance out of the antenna. Over here on this other loop, basically what I have is a box down at the bottom, which is containing two things. It's got the vacuum variable, but it's also got the separator, the bias T, because I feed the control signal and the RF over the same cable. And so both of those things are in here. The rule is the coupling loop should be opposite electrically where the capacitor is. There are very high voltages exist here and here at the top of the loop. And the same thing happens over here. This is a very high voltage point. This is a very high voltage point coming down this wire here. This thing should be right in the middle. And here on this part of the loop here is the middle right there. And that's why I put the coupling loop right there. So notice that although they're physically adjacent to each other, they're electrically 180 degrees apart. So that's the critical factor. And you'll see why that is true in a moment. But that's the way I handle that situation. A three-turn loop, any odd number of turns, the capacitor and the driving loop or coupling loop will be opposite each other physically and electrically. It's just the way things work out there. Okay, here's the example of a three-turn loop. This is the one that I use. I have been using even recently on 75 meters to converse with the guys on 3868. In this case, the bias T is down here at the bottom, and that's where the separation is done of the RF to feed the coupling loop, which is right at the middle here. And the capacitor is up here at the top. The breakout of the control signal, the DC control for the motor, comes right out of this box here and goes up through the middle of this pipe into this box. So that's shielded from view and from the weather. But anyway, the tuning capacitor there, the coupling loop down here. Okay, now the turns evaluation, I only show 3 here. As I've told you, 4 and 5, in my view, are a waste of time and effort. But if somebody wants to do them, I let the program do that if you want to, but I'm not going to waste my time. Single turn, 2 turns, 3 turns, and that's the only thing that's changing. As you can see with the single turn, the pitch factor is grayed out. There is no pitch. When you go to 2 turns, I have a 5 pitch factor. Same thing over here for 3. So I didn't change that other than turn it on when I went to a 2-turn or 3-turn coil. Notice everything is the same imperial. I don't change the circle or any of that kind of stuff. But notice what's changing. When I go from a single turn, I've got a Q of 676. I go to a 2-turn loop, that Q jumps up to 1828. And then I go to 3 turns, it makes a bigger jump to 2564. That's reducing. Notice I go from 10 kilohertz down to 3.88, down to 2.77 on the bandwidth. Well, let's look at that. It's easier to see this in the chart. And this is another one of the bar charts because it's easier to see what's going on. Going from a single turn to a 2-turn loop, you lose 2.2 dB. Dropping from 1 down to 3, you lose 4.4 dB, twice as much loss. And you can see the percentage numbers here. Again, this is percentage loss compared to a perfect antenna, of which there is none. But notice the other factors in here. You have the area. I just want to show you what's going on. The reason for these reductions is we're reducing the antenna factor, which is based on the incident area of the signals as they intersect with the turns of the loop. And you're going from 71.62 down to the 17.9 and then down to 7.9 here. That area is quite a reduction. And so think of what it would look like out here at 4 and 5. That's nightmare type stuff. Okay, I got to get rid of something here that's taking up cycles on my machine. Okay. Now, another thing to look at is the coupling loop. And there are a couple of considerations here. And there are several different types. The ARRL handbook, not antenna book, I'm sorry, not handbook. The antenna book shows the original, what's called the Patterson loop. This was done for the military around the Vietnam War time. Actually a little bit before that, but it was implemented in there. They used two capacitors, one which was a double capacitor with ganged plates, and then another capacitor in the middle here. One was tuning to resonance, the other one was tuning for the match. The problem with this is it's an unbalanced antenna. There's a coax feed in here. It's tied across this capacitor. The voltages in here get very high, and it's extremely tricky. You're riding on the back of a Jeep in the Vietnam situation, trying to adjust the tuning to get to the frequency you want to be on, and things are bouncing around, and it's a game. If you've ever used a capacitive tuner with two capacitors and an inductor to ground, you know what I'm talking about. You can do a dance there, and you can always find some kind of a match, but it may not be a good one. And you got the same situation here. You may get a match that gives you a decent SWR value, but your efficiency is low. And it's really hard to know whether you've gotten into the sweet spot or not. Another approach that was taken later on was this gamma match, and you can also do a T match, but that's a little bit harder to implement here. But the gamma match basically is a rod going out along the side, and it's actually not shown here, but there should be a jumper across here that ties it on, and you adjust the position at which that tie-in takes place, and that's how you adjust to get to 50 ohms or whatever coax value you're trying to match. And excuse me, by the way, the gamma match over here, it shows it really close, so you can have a little wider separation here. But the value of the match is adjusted by sliding something here and then nailing it down nice and tight. The sizes, the relative sizes of the conductors enters into the matching arrangement, as does the position there. And what you should do, if you have an antenna that's going to tune over 2 or 3 or 4 bands or whatever it is, do the adjustment of this to get the best match right in the middle of the overall tuning range, or in your favorite band, whichever one is more important to you. If you do it in the middle of the tuning range, you'll be able to go throughout the tuning range and get a 1.2 to 1 or 1.3 to 1 worst case, if you get a 1-to-1 match in the middle of the band, the tuning range rather. This other construction over here is a transformer. In this case, it's a 1-to-1 transformer, because one turn to one turn. The loop conductor itself being one of the turns, and this just being a shorted conductor around here that makes a single turn on the input side. That'll give you a certain kind of a match. You need pretty hefty ferrite cores here to do this, to make a transformer, because you're carrying the full power of transmission, and you can easily saturate those cores if you don't have enough. And if you do that, you can destroy the match, and you can also destroy the ferrites. Also, going from one band to another, you need a different number of turns on the primary in order to get a match of the same value that you had on the other bands. And so you'd need some kind of a switching arrangement here to choose the position of the tap to match the band that you're on to 50 ohms or whatever your coax is. So that's really a no-brainer. You don't do that. It just doesn't work. Some people have done it, and they claim it works, but it's not a very good way to go. Here's an example of a magnetic loop antenna, the AMA82. It's fairly popular in Europe, but this is one that has, notice, a relatively small, compared to the diameter of the main loop here, this is a relatively small diameter. And you wonder what's going on here. Well, it just turns out that with the relative sizes of the conductors, this size versus this size, and the placement, then the smaller the coupling loop can be smaller than the 20% that's typically used as a starting point. And I recommend, I emphasize that that's a starting point, not a rule to be used, you know, without exception. You can start there. Actually, I'd start a little bit bigger, make the loop a little bit bigger, because you can always shorten it easily. And you don't need to use a special shielded loop kind of construction. Those are real pain in the neck to build, and they're unnecessary. Just use a heavy conductor. I use the shield component of some RG141 coax that I have. It makes for a nice thick loop that holds its shape, and it's easy to position, and I'm done with it that way. It works out very easily. So anyway, a coupling loop it is what I say here, and then the questions become how big and where do you put it. I've given you the way I do it, and I'll show you some additional examples here as we go further along. This is an odd number of turns. Again, the coupling loop position. I'm just emphasizing what I told you a little bit ago. On this loop on the top visual, the coupling loop is way up at the top. The capacitor, the tuning capacitor, is down here near the bottom. And notice that there's some coax running up around the boom and going up through. There's a big RF choke on here. That's absolutely necessary for this type of arrangement where the loop is up at the top. You could flip this around the other way where the capacitor is at the top and the loop is at the bottom, and you wouldn't have to worry about that. Although it's still advisable to put a choke in the feed line. It's essential here. It's a nice to have if you're doing it the other way around where the cap is at the top. The electrical connection between them is not advised. In fact, as I say here, it's neither necessary nor advisable. It's an air core coupling between the main loop and the coupling loop. And I think everything else here I've already explained. Okay, very good. Here's the deal about the size on the coupling loop and why we say 20% diameter or length or whatever. The linear measures are easier to make. It's easier just to put the tape measure across there and say the diameter is X instead of trying to measure the whole loop and get the length, because that's a little bit more tedious. And what you're really trying to do is set an area. What we're really after is a ratio here, approximately 25 in area between the coupling loop and the main loop. That may go higher or lower depending on a couple of factors. However, if you have a couple of ohms of radiation resistance in the sweet spot where you're tuning, then 25 is the right number to use. And you can get 25 by either measuring the areas, if you know how to do that, or by making a simple measurement of length, diameter, or radius, and having a 5-to-1 relationship. Anyway, I recommend a 2-octave tuning range on these kinds of antennas because that gives you good performance even at the low end of the range. And so something like 14 to 28 megahertz, plus or minus a little bit of extra on one side there, that's a good range. Trying to go 10 to 30, and it is done on the MFJ antenna and several others, it works. However, it's stretching things to the point where on the low end, your SWR is going to get a little bit high. Your bandwidth is so narrow that you can't put a voice signal through it, although on 30 meters you won't do that anyway, at least not in this country, or you shouldn't. The digital modes, if you're going to be doing digital modes where they're in a 2 or 3 kilohertz wide bandpass, be sure to tune to the frequency that you're going to be transmitting on, not the one you're listening on. You can listen with the antenna tuned off frequency. You'll be able to hear okay, but you can't transmit if you're off by too much. And if you've only got a 1 or 2 kilohertz wide bandpass on transmit, and the signals that you're dealing with, the receive and transmit, are 2.5, 3, 4 kilohertz apart, then tune to the transmit frequency, and then everything will work out okay. And here's an example of receive versus transmit bandwidth. I'm using the 14 to 28 megahertz kind of arrangement. We're tuned to 14.076 megahertz. The RX bandwidth for this particular antenna, whichever one it was I was looking at the time, the 3D points, the 3 dB down, that's equivalent to an SWR of 2.62 to 1. This assumes that you've got a 1-to-1 match at the mid-band. If you don't, if your SWR doesn't come down that high, then you need to make the difference 2.62 kilohertz or SWR change between the lowest part and where you're trying to measure the 3 dB values. But notice that the TX bandwidth is not nearly as wide, or it's probably about half as wide as the receive bandwidth. This will give you a good clear reception of an audio passband for sideband, not so hot for AM. And this will be okay for really narrow band AM, but it's not very pleasant to listen to. And this is you transmitting to the other guys. They're going to say you sound like crap. So you want to be really careful about this. If you're working in a narrow bandpass part of the band or the tuning range of the antenna, go digital or use CW, which is the original digital mode anyway. Anyway, that's basically it on that. And the couple of pointers on my 2.3 program, version 2.3, I improved a couple of things. One is, in the earlier version, you could establish a project directory, but it was always under documents. Everything went to the documents folder, no matter what you were saving or trying to read. That's where it was going to be looking. And I've set it up now so that you can identify a project directory. Just in your directory hierarchy, create a directory for a particular antenna. And then when you save any information there, either save a design or saving the results of the export, you can put it in that particular place, just say where you want it, and everything will always go there from then on, and everything will always read from there until you change that by saving somewhere else or reading from somewhere else. And so you have control over multiple projects with ease now. The help system, I've improved it. The mouse wheel scrolling didn't work before, and that's something that everybody likes, including me. I shouldn't say everybody, but most people that I've talked to prefer to have that rather than having to reach over and grab the bar and slide it. The save design and load and export I mentioned all go to the project directory. This is a dialogue, not a dialogue. Well, it's a separate window that you go to where the help information is expressed, and you can resize it vertically, and you can use the scroll wheel on it. And even while you're running the program, you can go back in and work on the program and keep the help visible so that you can get help on whatever you're trying to do at the time. All of this stuff is available. Oh, the improved I/O security. Basically, I added a tag field at the front of the file information that gets saved when you do a save document, a save design, or that's it. Any save design will have the STL comma at the front end, and that's necessary because Malwarebytes was flagging the other tests that I had been doing to determine whether this was a real save design or not. It did the job well, but it was susceptible to somebody playing tricks if they knew what they were doing. And I haven't released the source code yet, but I'm going to be putting it on GitHub. When I finish up, let me see how I can say this. I'm a C language programmer from Bell Labs days. I learned about Unix and C when I worked at Bell up at 120th, and I used C language for a long time, and so there's a lot of C-isms, if you will, in the Python code that I've written. Some of them perfectly legitimate for Python code, as it turns out, but for a few of them I'd like to remove. And as soon as I clean up the code and am proud enough of it to put it out and say, I wrote this and I think it works pretty well, I'm not going to put it on GitHub, but I'll do that as soon as I can. The availability I mentioned, Windows. I say Windows 11 here. It'll actually run on earlier versions. However, I think Windows 7 no longer will run quite successfully, and there are some security issues there. And support is dying now for anything before 11. So I'm saying 11 here, and it will work to some degree with other versions, earlier versions, but I don't guarantee any performance that way. And Linux, of course, and then the Mac OS. These things are executables. What happens is when I make an executable, something that you can download and run on your machine, any one of these, it's an executable typically on the order of about somewhere between 9 and 11 megabytes. That sounds like a big program, but really what's going on is it's your code gets converted into bytecode. The bytecode versions of the library routines that I use are brought in, and then the interpreter tuned down to the level needed to run the code that's been created gets put all together in a module called the executable. That's why it's in quotes. It's really not, but you can treat it as if it were one. But it's really just running your code and the libraries in the interpreter that comes along with it. And unfortunately on the Mac, the executable size is now 20 megabytes. It was 40 until last week. And then they did an update to the PY installer program that I use to create these executable modules. And now it's down to 20 megabytes. And I'm hoping to get that down to 10 in the near future. But I've got to talk to the people who did the PY installer program. Anyway, that's basically it. Let me give you a quick summary here. These are the things that I think are important about getting good performance from these antennas. Capacitor, top of the heap. Good materials. I recommend copper. It's king in my view. Anything less than that. You don't have to silver plate it or gold plate it or any of that kind of crap, but copper is the way to go. And aluminum if you have to. I've done a number of aluminum antennas, loops that actually work pretty well, but their efficiency was low, on the order of about 40% off of what you can get if you use copper. The size matters to some degree in terms of the conductor diameter, but even a half-inch diameter will work. You can get better results with larger diameter, but you don't need to do it. It's not as critical as some of these other factors we've talked about. Single turn circle is the sweet spot in my view. That's the best way to go. If you have to use another shape or use more turns, do it, but do so grudgingly. If you can get away with a single turn circle, that's the sweet spot. And I mentioned this overall reduction in size as being the motivator for going to multiple turns. This may be necessary if you're trying to squeeze it into the back of a garage somewhere or in an attic. Hang them vertically, by the way. If you want to use one of these things horizontally, you can. But if you do, you've got to get it up to dipole height to have it have any benefit. Down low, it's just, it's omnidirectional, but it's not going anywhere. It's mostly straight up. And so you want to be careful about that. I recommend you hang them vertically. Use the nulls to try to minimize noise coming in on reception. And otherwise just go for it. The careful sizing and positioning of the loop, I tell you here, you can make a good antenna, but it's got to be properly balanced. That means a couple of things. When you think about the coax coming in and going into the loop and then going around and coming back out, that's a nice one-way path for any cycle, and then the opposite on the other half cycle. and you don't really need to do much in the way of calming that down. But if you try to use something other than the coupling loop, the kind that I showed you earlier, you're going to have to choke the coax, and possibly in more than one spot, right at the antenna perhaps, and also right where it enters your home or wherever your radio is, maybe another choke on that side. Anyway, that's basically it. The last slide here basically just shows you how accommodating my wife has been. I'll stand by for any questions if you have any, and otherwise you're free to be returned to society.
Nope, no questions from the room here.
Okay.
Yes, thank you.
Yep. Just drive carefully wherever you're going.
Will do. Will do. Thank you again.
Okay. Good night. Thank you.
Mm-hmm. All right.
Thanks to Peter, we're going to do, I think, we got planned 4 DRC Saturdays. So do four DRC Saturdays. Is the POTA the first one? Yeah. So we'll get a email blast out, and it'll be in the roundtable and on the website. But anything else? Yes, sir. I don't have the.
We had about 711 contacts. I think it ended up about 2,500 points when I submitted it. So, but yeah, about 711 contacts.
And I will say one thing about that. I kind of harped on we needed a lot of help, and you guys turned out. It was pretty impressive, I think, compared to other years, especially our teardown. We quit at noon like we supposed to on Sunday, and at 5 minutes to 1, we were packed up and headed out. That was really fantastic to get that all. The kitchen was packed up, the tents were down, tower was down, antennas were packed, and so if you came and helped, we do appreciate it. Thank you. And unless there's a question for me or about the club, yes, sir. Yeah. Orland's friend Ted from Texas, he operated all night. I think Orland stayed up pretty much all night. And you stayed up all night. Yeah. So we did, worked out great. It's a nice spot to do it. Other than it'd be nice if we had trees, but we don't. But it's convenient, and there's enough room, and so. Kevin, you got anything to say? Anybody? Yeah. Yeah, we need net controllers. Just take it, once a month or whatever. Say again? You're okay. Bill's up Sunday night, so thanks for that. And can you think of anything else, Kelly? No, any membership stuff? No. If you don't know, Kelly's doing our membership and doing a great job at it. I do need to talk to you about something before we go. Thanks for coming.
Thank you much. And we're signing off on the side. Yeah, it worked out well. So thank you for getting the meeting set up and doing all that part, Jerome, too. Thank you.